done with my dentist appointment. I should have, but I'm not going.
You can do it. I might. But it's fine. Oh, your friends got it though.
I might just forget an accident, but really on purpose. So.
I'll go. I mean, I'm planning.
I'll remind you.
The molar would equal the concentration times the partial. That's supposed to be like theta.
Sorry.
Theta of the mixture equals the summation of xi times the partials. As you say,
When I'm sitting at night in the dark, you can't see how big it is.
Oh yeah.
Did you do the face?
He's calling me weird.
No, he said he's going to go to the right to the
I did most of it. No, I did support the second half too. I did for number 4.
That's a really weird.
Yeah, I don't think it's too shitty for it to be.
It was a brownie. It was a very good thing by me.
It looks like a cosplay.
It's like for number 4, they use this relationship, and then they give you another relationship for that. So you just set them equal, and then those cancel out. You look at just that.
I was wondering what we were supposed to do when I said it.
Don't ask me about those 3 that were reading these question marks, but
Wait, what did you do? You said.
So what do you do?
use that relationship.
You go to this website.
Combination of it. You set equal, and then it cancels out as you are.
I knew it was going to cancel. Somebody has to.
And so you play.
Sneaky. Oh my
And
god.
you pick what you want to compare.
It all makes
And
so
then you
much
play.
sense. Like at the beginning.
So which one has
Yeah,
the
they give
It's
you
like
A
S1
minus R
equals
log x1.
Oh, it's one made.
But this one I can't even figure out.
And then you set it
Yeah.
to this.
Yeah, but they're kind of hard. You like,
Well, we were trying to
so
do.
you have to get
I haven't seen anything.
a 20 out of 20. Yeah.
That's basically what this is. Delta makes sense is what that is.
But it just like wasn't fun.
Yeah.
Pretty much.
Me? How many times do I have to do to get it?
It only
Twice.
took him once
That's
the
good.
papers, so that's it.
I know, but like. No, they give it to you at the end.
Oh.
I wrote this thing.
So it would take any one person twice.
Maybe one person who's got to choose.
We found six.
Yeah. Oh, and the person.
I was, cause he like, I was like watching
Yeah.
that equation.
I mean, I've already
And I was
won.
so like,
Oh
how
my
do you use that? And then I like, he kept saying.
So then they give me this. What I do is I take a picture. Oh.
Yes, I did like, that's just.
Oh, yeah. I would.
No.
I mean,
No.
Yeah, I just want to know.
no.
I just wanted to know though. So
It's like when you're looking at.
I did it once and then I took a picture of the ingredients and then I did it again.
If x1 is on your x-axis, I thought
Really? Really?
You can be as wrong as you want.
I mean, listen. Wow. I didn't try that. I just assumed, yeah, I just assumed that you needed to.
No, I got like 6.
Huh. Well, that's crazy.
So.
I'm gonna use
My
this.
dad. Well, they didn't email though.
Yeah, but I.
Yeah, my dad did. And he was like, "You ready to message real soon? Just send it back to me." So I got it.
See, they won't let you do it. Yeah.
All right, folks.
Kind of like private browser.
I mean, hopefully the rest will make sure. I've never even had it. So.
And that's what's just like, we had it. I know.
I like those. But
just sit there.
I've never had it. So I can't compare.
No, it was like.
So we left it.
So today, we'll continue with the Nyquist stability criteria. Okay?
doing all exam problems, and I checked, everything has been posted. You have plenty of exams to study. Material for this exam starts from getting first order plus time delay models from response curves. Okay? And computer is absolutely needed in this exam. Obviously, we can do nothing without the class program that gives us Bode and Nyquist plots. I did manage last semester to make an exam which didn't require computers, but I don't think that will be the case. Very small chance of that, okay? So I will make the final announcement if it will be computers or not on Monday. Okay, but 95% chance it will be with computers. Okay, which means also you should know how to get transfer functions using minimization of the sum of errors squared using solver. Okay? That is actually I cannot examine without computers, but since you don't like to do that, then we use computers. Okay? All right. So let's continue where we left off last time. And remember, we have two plots I've been working with. One is the Nyquist path, which is what S is doing. And if I have no integral action, then the Nyquist path has three portions. We're going up on the imaginary axis starting from the origin. And in that path, which I call C plus, S is plus I omega. Once we reach infinity, as Josh recommended, we take an infinite radius semicircle to bring us to the other side of the imaginary axis. So this is the CR. This S is limit as R goes to infinity, R into the R theta. And then we have the return to the origin. And here is C minus, where S is minus I omega. So that's the Nyquist path. The whole idea behind it is that it's a closed path, a closed curve, that it would include inside it any positive root, any root with positive real part, either numerator or denominator. Clear? Anything with positive real part would be inside this closed curve. The Nyquist plot is what GOL of S, and if I create new nodes and said I decided I'll be referring to GOL, even though it has GOL, I'll be referring it as G loop. It's the product of all transfer functions in the loop. So a better name for it would be to call it G loop. But you have all my nodes and say with GOL, or previous things with GOL, okay? So we have a Nyquist plot. And that is what GOL, which in standard class notation is GUGC of S, okay? Does as S travels in more mathematical terms, is the mapping of S through GOL as S travels the next. And that will have x-axis is the real part of GOL of S. Y-axis is the imaginary part of GOL of S. And we'll have some kind of curve. If there is no integral action, we'll be starting actually typically from somewhere in the positive real axis. And we will have a plot like that. That will be the mapping of C+. And that's what we can get directly from a body plot. CR maps just at the origin. To be precise, a semicircle maps to semicircle, but the infinite radius semicircle maps into a zero radius semicircle. And here, GOL of S is GOL of plus I omega. For C minus, GOL of S is GOL of minus I omega. So GOL of minus I omega is take GOL of plus I omega and replace plus I by minus I. That means the two things are complex conjugate.
You said that one starts on, it doesn't start at the origin, right?
No, yeah, it starts at the origin.
It does?
Because remember, here you start to go from omega to infinity, here you go from infinity to zero.
But that
from
one.
zero to infinity. But it's the mirror image of this spiraling in this case out from
Wait, the CT, where does CT negative start? C plus.
C negative.
No, C plus. Where does C plus start? The origin or the?
No, C plus starts.
Okay, that's what I want to know. Thanks.
And in the software, you have different colors. So you pay attention also, it's drawn. Always starts with C plus. So you know which is C plus. C plus ends at the origin. C minus starts from the origin. Okay? So
why here C minus down and C plus? Is it
it's a closed curve. Okay? It's a closed curve. You go from zero, optimize to infinity. Once you reach infinity, you come to the semicircle to minus infinity, you go back to zero.
But always here C minus the top and C plus.
No, not necessarily. It's the other way around. Okay, you have to watch what the plot is doing. All right. So, time for the Nyquist stability criteria. Many years ago, I used to do the full proof of the Nyquist stability criteria. It was taking about 3 lectures. It's one of the things I'm not doing anymore. But I will at least demystify something about it. So I will give you just small part of the proof. If you have taken a good complex variables course, you would have learned the following theorem, that if I have a complex function, if we have a numerator, denominator, whatever, okay? And I draw any closed curve in the S plane. Here is real part of S, here is imaginary part of S, okay? And take any closed curve. Okay? And inside that closed curve, I have denominator roots, or things that make that f go to infinity, or d go to 0, and numerator roots, which make f go to 0. Okay? And let's put x's for the denominator roots of f. Whatever, okay? And let's put o's for the numerator roots. Okay, with me?
No.
So x
No.
x is denominator
Okay.
roots of f. O is numerator and I have a path that is clockwise. I travel as clockwise. Okay? So this is what I'm doing with S. Okay? Everybody understands? S is some complex variable that travels a closed curve in the plane. Here's real part of S, here's imaginary part of S, so I have some kind of closed curve. And inside that closed curve are some numerator roots and denominator roots of f of s. With me? Then you have the following result. The number of times f of s, so as s travels, f of s does something. So f of s, so this is what s does. Here's what f of s does. Here is real of f of s, here is imaginary of f of s. And f of s will do something that will enclose the origin. So f of s might do something like that. Okay? So the number of times f of s encircles clockwise. That's what I forgot. Got to bring string. Yes, I do have a string.
Yeah, you can use this.
I do have a string.
Oxus Piranhas.
My budget code. My budget code for giving the backpack. My budget. So number of times f of s encircles
But it's so small.
clockwise the origin. So it encircles the origin, okay? Is equal to number of numerator roots of f minus number of denominator. So if I had here, like in this example, how many numerator roots I have?
1, 2, 3, 4, 5, 6, 7.
Well, actually, how many? Well, I wish, okay, please, I want to change my notation. I want to make the x's the numerator roots and the o's the denominator roots. So please change the notation, sorry for that.